Good morning, students. Let's start with the next topic. In the last video we have seen problem of the deadlock as well as what are the characteristics should be there. There were 4 characteristics, that is mutual exclusion, hold and wait, no preemption, and then no circular wait. These were the 4 characteristics should happen simultaneously, then there can be a deadlock in our system. So let's continue with the next topic, that is resource allocation graph. So in this case already we know how we can use the graphs. We know graph is nothing but set of vertices and set of edges. So in this case vertices are divided into 2 parts. One is a set of processes, another one is set of resources. Processes is nothing but how many processes you will use in the system and how many resources we are having in the system. Then one more thing we need to understand here is request edge and assignment edge. The request edge is nothing but there is a directed edge from process Pi to resource Rj. That is nothing but this particular process is requesting the particular resource. Whenever any process is requesting the resource, so then there will be a directed edge from process to the resource in the resource allocation graph. Then coming to the assignment edge, in assignment edge there will be a directed edge from resource to the process. That means this particular resource is already assigned to the particular process. So that is the meaning of that. Let's go ahead. Process is represented by circle, resource type is represented by square. These 4 dots indicates how many copies of that particular resource types are available. As we already discussed, 4 copies are available with respect to this figure. Then already I said there is a directed edge from process to the resource. That means this particular process is requesting 1 copy of the resource Rj. Because 4 copies are available, 1 copy it is requesting. Then if there is a directed edge from resource to the process, 1 copy of the Rj is already allocated to the Pi. So this is how. Next, coming to this diagram, this is a one example of resource allocation graph, how we can draw. First we have to list all the processes available, then we have to list all the resources available. As already told, all the processes will be represented as a circle, all the resources will be represented as a square. Then number of instances or number of copies will be represented with a dot. That means R1 is having 1 copy, R3 is also having 1 copy, R2 is having 2 copies, R4 is having 3 copies of instances or 3 copies of resources. So coming to the graph, so resource R2, there are 2 copies, 1 copy is given to P1 and 1 copy is already assigned to P2. Because there is a directed edge from resource to the process, then it is called as assignment edge. That means 1 dot is given. 1 dot means 1 instance is given to the process P1, 1 instance is assigned to the process P2. But there were 3 instances of the R4, it is not allocated to anyone, it is available in the system itself. Then P1 is already having 1 copy of the R2, P2 is already having 1 copy of the R2. 2 were available, all 2 used for the P1 and P2. Next P1 is it will start with execution, but to complete the execution P1 requests one more resource, that is R1. But how many copies are available? 1 copy is available for the R1. Whether it is available? No, it is not available, because the 1 instance was available. That 1 instance is given to the P2 already, because there is a directed edge from resource to the P2. Then P1 will go to the waiting state, because it is not going to get R1 immediately, then it will go to the waiting state. Then P2 is already holding R2 as well as R1. Then what P2 will do? He will start executing, but to complete the execution he needs resource R3 also. Then he will request resource R3. Whether resource R3 is available? No, because it is already assigned to the process P3. Then whether process P3 is executing, it will start executing. Whether it is depending on anybody else? No. Then he will complete the execution with the help of resource R3. Once he completes, he release the resource R3. Once he release the resource R3, R3 will be given to the P2, because it was waiting for the R3. Then P2 will complete the execution. Once P2 completes the execution, he release the resource R1. For that P1 was waiting. Then P1 will get the resource R1. Then P1 completes the execution. So this is how the execution will get complete. Is there any deadlock in this system? No, because P3 is independent. Once P3 completes the execution, P2 will get complete. Once P2 completes, P1 completes. So none of the process are going to remain incomplete. All process will complete with a okay. Let's see another example where we can get a deadlock. See here, the same example is modified little bit. P1 is requesting a resource R1, R1 is already with P2, P2 is requesting resource R3, R3 is with already P3. But P3 is in turn requesting the resource R2. How many copies of R2 were available? 2 copies were available. One is assigned to P1, one is assigned to P2. How many are available then? 0 are available. When P3 requests 1 copy of R2, it is not having any more. Then P3 also will go to waiting state. Already P1 has went to the waiting state by requesting R1. P2 has already went to the waiting state by requesting R3. Now P3 is also going to the waiting state by requesting R2. Then who will come out of the waiting state? None of them, because P1 is waiting for the P2 to complete, P2 is waiting for the P3 to complete, P3 is waiting for the resource R2 which is held by P1 and P2. Then indirectly P3 is waiting for either P1 or P2 to complete. Nobody will come out of the waiting state. So this situation we call it as a deadlock. So let's see with a cycle here. P1 is dependent on R1, but R1 is with P2. P2 is dependent on R3. R3 is with P3. P3 is dependent on R2. R2 is with P1. Then there exists a cycle here. This is a one cycle. P3 is dependent on R2. R2 is with, this is one cycle. Then another cycle exists in the system, that is P2, R3, P3, R2 and then P2. Then total there exist 2 cycles in this system. Whenever there is a cycle in the resource allocation graph, then there can be a deadlock. So that is the meaning of resource allocation graph. In this process, even P1 is not able to complete, P2 is not able to complete, P3 is not able to complete, because P1 is waiting for R1 which is with P2, P2 is waiting for R3 which is with P3, P3 is waiting for R2, R2 is with P1 and P2. Nobody is going to release because they are doing hold and wait. Then none of them will come out of the waiting. Then nobody will complete the execution. So let's see graph with the cycle but no deadlock. In previous case there were cycles in a graph, so we said there can be a deadlock. But in this case there is a cycle but still there is no deadlock. That is because we have multiple instances of the resources. In previous case we had a single instances for most of the resources, but in this case there are two resources, both are having multiple instances. So P1 is requesting resource R1. How many copies are available? 2 copies are available, but both are assigned to P2 and P3 already. So no instance is available, so P1 will go to the waiting state. Then P3, whether it is waiting for anybody? Yes, it is waiting for the resource R2, but resource R2 2 instances were there. Both the instances, one is given to P1 and one more is given to P4. So in this case also there exists a cycle, that is P1 is depending on R1, R1 is already given to P3 and P3 is requesting R2, R2 is with P1. There is a cycle but no deadlock because P2 completes the execution. It is not depending on anybody else apart from the resource R1. Once it completes the execution, it releases the R1. Once one instance of R1 gets released, that one instance will be given to the P1. Once R1 gets released, P1 completes the execution. Once P1 completes the execution, it releases the R2 also. Once it releases the R2, R2 will be given to P3. Then P3 also completes the execution. In this case, in this graph, there exists a cycle, but there is no deadlock. The only reason is we have a multiple instances of the resources. So if you have a multiple instances of resources, then the possibility of getting a deadlock is less. If you have a single instance, then the possibility of deadlock with the cycle will be 100%. Let's go ahead. So we'll come to the conclusion. If graph contains no cycles, if there is no cycle in the graph, then deadlock will not be there in your system. If graph contains a cycle, if only one instance per resource type, then there can be a deadlock. If several instances per resource type, possibility of deadlock will be less. So this is what the conclusion. If no cycles, no deadlock. If there are cycle, then there are two cases. If the number of instances or number of copies are 1, then the possibility of deadlock will be there. If number of instances are more, then the possibility of deadlock will be less. We have seen with the help of example. Okay, let's go ahead. Next, one more important topic, that is methods for handling the deadlock. There are n number of methods. Ensure that system will never enter a deadlock state. That is nothing but we should take a prevention so that it will never enter to the deadlock situation. Allow the system to enter a deadlock state and then recover. We can recover it. Then ignore the problem and pretend that deadlock never occurs in the system used by most of the operating system, including Unix. This means even though if deadlock occurs, we should pretend that deadlock has not occurred and it has not created any problem for me. And most of our operating system do this only. Next, coming to the deadlock prevention, because already we know that prevention is better than cure. We can make our system not to enter the deadlock by taking a preventive measures. Already we have seen what all the characteristics should happen simultaneously in order to deadlock to occur. One is mutual exclusion, hold and wait, no preemption, and then circular wait. If you make any one of these condition false, then your deadlock is prevented. So first condition, mutual exclusion. Mutual exclusion is nothing but only one process should access the particular resource at a time. That is nothing but only one process can use one resource at a time. That means no other process are allowed to use the one resource at the same time. This holds good for the non-shareable resource. In case of shareable resources, for example, printer is a shareable resource. If you give printer for only one person, then there is no meaning. You can share among the multiple. So in case of shareable resources, what we can do is we can make mutual exclusion false. If we make mutual exclusion false, then the non-shareable resources can be used by multiple processes so that the deadlock possibility will be reduced. Next, coming to the hold and wait, means we should make mutual exclusion false for non-shareable resources at least. For shareable resources we cannot do anything. In shareable resources we can make mutual exclusion false. In non-shareable resources mutual exclusion should be there, because at a time only one process has to use that non-shareable resource. For example, file can be used by only one process at a time. It cannot be given to the multiple processes at a time. So that is how the non-shareable resource works. In case of shareable, like a printers, we can give it to the multiple processes at a time. So in case of shareable resources, we can make mutual exclusion false. Then the deadlock can be prevented. Then second condition, hold and wait. In this case, but actually in order to happen with a deadlock, hold and wait, most of the processes will be holding some resource and they will be requesting some more resources. But in this case, in order to prevent the deadlock, what we can do is we will ask all the processes to release the holded we'll ask all the processes to release the existing resources what they are holding, and then we can allow them to request for the new resource. Then definitely hold and wait will become false. That means if they want to get any new resource, then they should release all the existing resources what they are holding. Then only they are allowed to request a new resource. So that you can make a hold and wait false. Then possibility of preventing a deadlock will be more. Then coming to the no preemption. No preemption is nothing but once they get a resource, they will not release the resource in between. But what we can do is, in this case, we can ask the processes to release the resource if they don't get the requested resource immediately. Now assume that process P1 is holding the resource R1 and P1 requests one more resource R2. Whether R2 is available? No, it is with somebody else. Whether P1 is going to get that R2 immediately? No, then P1 has to go to the waiting state. So in this case, if the process doesn't get the requested resource immediately, in that case it should release the existing resource also. So that is nothing but it is doing the preemption. It is releasing the resources in between. Without completing also the process has to release. That means we are making no preemption false here again. Then if you make this condition false, then the deadlock happening will be less. Then the circular wait, that is nothing but you should make sure that there should not be any cycle in your system, so that circular wait also will become false. In characteristics, what we have seen, all these 4 conditions should be true, so that there can be a deadlock in your system. But in prevention, we have to make this condition false. Any one of these conditions can be made false, so that your system will never enter a deadlock. So this is how we need to explain. Then we need to understand what do you mean by. We'll come back to the deadlock avoidance later, how we can avoid the deadlock. Before that, we'll try to understand safe state. Safe state is when a process requests an available resource, system must decide if immediate allocation leaves the system in safe state. For example, if P1 requests any resource, if it gets the resource immediately, then the system will be in a safe state. Then, what do you mean by safe state? One more thing we need to understand. Now assume that to complete execution of multiple processes, there exist a multiple sequences. For example, we'll try to understand with a simple example with respect to our college. From SGBIT to go to the CBT, we have multiple paths. One, we can go directly to the Kolhapur circle, then Chennamma circle, then CBT. Then one more is we can come from SGBIT, SP circle, then RTO, and then CBT. There are 2 paths available. One path is having too much of traffic, another path is having no traffic. Then which one we will choose? We will choose the one which is having a less traffic. So safe state is nothing but in which order, if you execute the processes, then the possibility of deadlock will be less. So that path we call it as a safe state. If you execute the processes in order P1, P2, P3, P4, then there will be a possibility of deadlock will be less. If you execute the processes in order P1, P4, P5, P6, then the possibility of deadlock will be more. Then which one we will choose? Then definitely we will choose the first one. Then how to decide this safe state? We will see with the help of algorithms later. Safe state is nothing but choosing the sequence of process execution in such a way that if you choose that sequence, then the possibility of deadlock should be less. So that is what we call it as a safe state. If a system is in safe state, then no deadlock. If a system is in unsafe state, then the possibility of deadlock. Ensure that system will never enter a unsafe state. We need to take care that system will never enter a unsafe state by considering safe states. Then this is a diagram. Most of our systems will be like this. Safe states will be more and unsafe states will be less. So always we should try to execute our system in this area only. If we enter this area, then possibility of deadlock will be there. I am not saying that 100% deadlock will occur. Possibility will be more. But we should always try to execute our system in this kind of area. So that is safe state. Means whatever the paths are available here, these all paths are safe. Whatever the paths are available here are risky paths. You can complete it, but there are risky paths. Next, avoidance algorithm. We'll see this avoidance algorithm in the next video, because from this banker's algorithm we'll get one 10 marks problem in the exam. For that we will have a separate video. Thank you.